Okay, so in order to complete that list that I started of elementary functions, remember we had the polynomials, quotients of polynomials, which we called rational functions, trig functions, and exponential functions. In order to complete that list, I want to add to it all the inverse functions of those functions. And you've met them. You've met, for example, the logarithmic functions. Those are the inverse functions of the exponentials. You've met the inverse trig functions, arctan, arcsine, and so on. You've met inverses of polynomials. What's the inverse of x squared? Root x, right. So what I want to do now is define, wait, one second. I want to define what it means for a function to have an inverse function, and what is an inverse function. And then to study when those inverse functions exist, and that's going to be related to these two things that we ruled out. And then I can complete that list of elementary functions. So, the idea of an inverse function is really just undoing what f does. So here's f. F somehow takes this x in the d potato and sends it to y in the e potato. An inverse function is a function that undoes this. So I want a function that if I tell it here, take y, it will retrieve x. I want a function that goes the other way. I want a function that does this. Okay? And a function that goes the other way is going to be called an inverse function. I'll write a formal definition in a minute. And the notation for it is going to be f with a little -1 up here. And it's going to be called f inverse. That's the terminology. Now, if I want a function that does this, my claim is that those two phenomena of being not one-to-one and not onto cannot happen with f. Why? If f is not onto, if there's a y here that didn't come from some x, then f inverse would not know what to do with that y. Right? I want the inverse function to take anybody here and send it back to where it came from. Right? But if it didn't come from anywhere, how could it send it back? Do you agree? Do you see what I mean? So if somehow in the definition of an inverse function, it's going to imply that the original function was onto. Do you understand that? Likewise, if for some reason this y guy had two arrows coming into it, what would f inverse do to y? Where would it send it? Would it send it to x1 or to x2? How would it know? Can it send it to both? No, why not? Has to be unique. If f inverse is going to be a function, it cannot map y to two different x's. Right? So both of these things, having a y with no source and having a y with more than one source, cannot exist if we want there to be an inverse function, a function that goes the other way and retrieves the original x's. Does everybody agree to that? Yes?
So would it be like saying that we take y as a function of x, the inverse function?
Let me write the definition. I didn't write it yet. Let me write the definition. But do you get the idea? The idea is going back. That's all there is to it. Okay? So let me write the definition. It's going to be a mouthful. You're going to have to read it more than once to get used to it, because it's going to involve the domain and the range. Let f be a function from D to E. Okay, so we're taking a function with a domain and a range. We say that f is invertible if there exists a function, which I'm going to right away denote by f inverse, and f inverse goes from E to D. So if there exists an f inverse going backwards from the range of f to its domain, from E to D, such that, so far I just said there's a function going backwards, but I want to say that it really undoes what f did. Okay? So such that for any x in D, if I take x was in D, if I do f to it, where do I land? In E. And to that I do f inverse. This is composition. I do f inverse to f of x. Do you recognize that there's a composition going on here? What should I get?
X.
I take x, I do f, and then I do f inverse. What should I get? X. This is saying that the function undoes. And likewise, and for any y in E, so if y started off in E, I can take y, I can first send it back to where it came from. Where do I land? I take a y in E, I do f inverse to it. Where do I land? In D. So now it's something in D. I can do f to it. And where should I eventually return? To y. Very good. Okay. So, again, this is a mouthful when you see it at first. You have to read it more than once to grasp it. But all that it says is what I drew here on the picture. If you take an x, so this cannot happen if you want it to be invertible. So these two things cannot happen. So this doesn't happen and this doesn't happen. And all that this says is, take an x. We don't need the indices anymore either. Take an x, do f to it, take the result, do f inverse to it, you get back where you started. That's this statement. Likewise, take a y, first do f inverse to it, to the result do f, you get back where you started. Y. That's the undoing part. That's the idea of being inverse functions. Okay? Clear? Is the definition clear? Okay. Let me just add f to the minus 1 is called the inverse function of f. So this is what it means for a function to be invertible, and f minus 1 is called the inverse function. So let's do a bunch of examples. Maybe before the examples, let me, graph-wise, how does it look on the graph? So suppose I have a function. Here's a function. Let's start off with something we know well, x squared. Do you agree that this is x squared? Why did I draw only this half of it? Why didn't I draw the other half? Right. If I drew the other half, it wouldn't be 1 to 1. There would be two x's with the same y value, like 3 and minus 3. Do you agree? And then the inverse function wouldn't know what to do, right? So I have to draw only one half, and now it's 1 to 1. It's okay. So saying that a point is on this graph. What does it mean that this point here is on the graph of x squared? What does it mean? Why did this point land on this graph? Because this x gets mapped to this y, which is precisely x squared. Do you agree? So a point xy is on the graph if y is x squared. That's what we graph. Does everybody see that? Yes? All the points are on the graph are of the form x squared. Does everybody agree to that? That's what it means to be the graph of x squared. Right? Say yes, everybody. I see some suspicious looks here. What's he talking about? This should be very clear. Everybody good? Okay. So what do we want the inverse function to do? We want it to take x squared to x, right? So points on the graph of the inverse function should be of the form, instead of x squared, should be of the form x squared x. Do you agree? Do you agree? So the x-coordinate of points on the graph of the inverse function should be squares of the y-coordinate.
But that makes not the function.
Well, if your x's are only allowed to be positive, then everything is fine.
Yes.
That's what we took.
Ah, okay.
Okay, so the inverse function, orange to the rescue, thank you. The inverse function, so if this was a point on the graph, let's say this is 3, 5. No, that's not a point. 3, 9. Right? 3, 9 is a point on this graph. Do you agree? Then 9, 3 should be a point on the inverse function's graph. Do you agree? So for any x f of x, we would have the 9, 3 would correspond to 3, 9. And if we map all of them, what we would see is that we would get precisely a mirror image with respect to the line y equals x. The graph of the inverse function is going to be a mirror image with respect to the line y equals x. It's going to look something like this. Well, this should have passed. Oops. We can fix this. Or can we? That's better. Okay, so this was... Because for any point AB, the point BA should be on that inverse function's graph. So in general, maybe I can erase, I mean, it is x squared, but in general, this is going to be the picture. This is f inverse, where this is f, and the way we see it in the picture, in the graph, is f inverse being the mirror image of f with respect to the diagonal. Did everybody understand this? Okay.
The second point is x squared x, you're saying?
This is x squared x, or another way of saying it is x root x. Right? And this, if this is x squared, its inverse function is root x. Do you agree? Okay. Let me write a theorem. I'm not going to prove this. We argue this, and then I'll do all the examples. F is invertible if and only if f is 1-to-1 and onto. Okay, I won't write the formal proof of this theorem. That would really could confuse some of you. I don't want, it's not necessary. I want you to understand the idea. For f to be invertible, for me to be able to map back, it cannot be not 1-to-1, because then I have a guy that came from two different people. I don't know where to send him back. And it cannot not be onto. I have a guy that nobody was sent to him. I don't know where to send him back. But if it is one-to-one and onto, then every guy in the range came from a unique person in the domain. I know exactly where to send him back. Good? Is the idea of this theorem clear? Let's do a bunch of examples now.
You say repeat that again?
Yes, that would be repeating it for the third or fourth time, but that's fine. A function is one-to-one and onto means every guy in the range, we still have it here, every guy in the range, if a function is one-to-one and onto, has only one arrow going into him, and has that arrow. This does not happen, and this does not happen. That's what it means to be one-to-one and onto. In that case, if it's one-to-one and onto, I look at a y, I know exactly where to send it back, to the unique x it came from. Good? Everybody? Yes?
So we could always restrict the function to make it one-to-one or...
Not always. Sometimes we can. Okay? Let me write many examples. Okay? And then maybe some counter examples, the functions that are completely hopeless, that for which we can do nothing to... Okay, so maybe it's time to erase this. So I'm going to write the formulas. When I say an inverse function, you should be able to do two things. You should be able to write the formula for the inverse function, which that you do by just solving the equation of the function for y. Did you do things like that? Okay. Or you can graph the inverse function just the way we did that. Mirror image with respect to y equals x. Let's do some of those. So, examples. So here's example 1. I'm going to take the function e to the x. So I'm going to draw the original function in blue and the inverse function in orange. So this is what e to the x looks like. Remember? The first thing I need, if I want to ever have an inverse function, is I want it to be one-to-one and onto. Is this function one-to-one? Can there be 2 points, 2 x's with the same y? No, this function is one-to-one. Does everybody see that? Just off the graph. Yes? Do you see why it's crucial that when I say e to the x, you see this? Do you understand why it's crucial to know these graphs? Okay. Is it onto? It's not onto the reals, but I can restrict the range and declare the range to be what? Just the positive reals. Do you agree that if the range is just the positive reals, then it is onto? Do you agree? Good. Now it has an inverse. That inverse I can draw. The way to draw it is draw y equals x and take the mirror image. There it is. Do you agree that that's the mirror image? You should look from here and see a symmetric picture. Do you see that? Again, you should look from here and see a symmetric picture. Okay, and do you know what this function is called? Right, this is the natural log of x, ln of x. Good? That's the inverse function. What does it mean that it's the inverse function? This precisely means, that e to the power ln of x, you take x, you do ln to it, then you do e to that, what do you get? X. Or likewise, if you take ln of e to the x, what do you get? X. That's what it means for these to be inverse functions. You compose them in either way, you get back where you started. Or you can write this for y if you want. You can write y here and y here. It doesn't matter. Do you agree? Do you know these facts? Okay, maybe you just learned them as facts when you learned about log functions, but that's what it means. Everybody good? Here's another example. Let's take, well, we did x squared and root x over there. Okay, let's let's do that, just so we have the entire collection. So I'm going to take all these caps and put them here and hope I don't get dirty. Okay, so here's x squared, restricting the domain so that it's 1 to 1 and onto. Here's root x, the inverse function.
If we didn't restrict the domain,
It wouldn't have an inverse. If you would have taken the entire x squared, the mirror image would be something like this, a parabola sitting like this. Do you see that?
yeah, that's not true.
But it's not a function.
I cannot use this, right.
Right? I mean, you would try to, if you would try to allow this entire thing, which is not onto, but suppose you were naive and tried that, what you would get as the inverse is something like this. But this orange thing is no longer a function. It doesn't pass the vertical line test. There are x's that get sent to two different y's. Do you see that? Everybody? So that's why it's a big no-no. That's the whole idea of what I'm trying to explain in this discussion. Good? And again, what this means is that if you take the root of x squared, what you get is x. Not plus minus x. X, and this is only defined for x's which are greater than or equal to 0. Clear? The root of 9 is 3. It's not plus minus 3. It's only 3. Good?
Why you're saying that?
That's the definition of the root function. It's the inverse function of x squared. It's not true if somehow you learned in wherever in high school that the root of 9 is plus or minus 3. That's not correct. The root of 9 is 3. Okay? It's true that minus 3 squared gives you 9. That's true. That's because x squared is defined on the entire real line. Okay? But root x can only send you to positive y's. Okay? Clear? Did I shock anybody now? Yeah, huh? Can you live with that? Good. We move on. Life goes on. Okay. Here's the next example. I hope in between the lines you appreciate the fact that properties of functions depend heavily on the domain and the range. It's not just the rule. Okay? This should be an important lesson from this entire discussion. Okay, here's another one. Here's x cubed. Is it 1 to 1?
Yes.
Yes. Why? Tell me automatically why. Right, it's monotone, strictly monotone increasing. Do you see that? And that was a statement we had. A strictly increasing or strictly monotone function is always 1 to 1. But do you see from the picture that it's 1 to 1? Is it onto?
Yes.
Yes. Every real number can be obtained as a value of x cubed. Very different than x squared. So we don't need to restrict the domain. We just need to draw this y equals x mirror here. And draw the mirror image, which we're going to call, what's its name going to be? Right, cubed root of x. That's this orange thing. Can you see the orange and the blue? Can you see the difference? I don't need to draw them on different graphs, right? Okay, here's another example. Let's do sine. Example number 4. Let's do sine of x. What do you know in advance that I cannot do? Take the whole function, right? If I took the whole function, look up here a second, and let's just do this without putting this nonsense for real on the board, just waving my hands. Suppose you think of the whole function sine. What would the inverse function look like? Something like this. Do you agree? That's not a function, right? Do you understand what I'm saying? Good. So what I need to do is first restrict sine only to an interval where it's 1 to 1 and onto. We did that before. So this is sine. Let me make this picture a bit bigger, because there's some accuracy to observe here. Let me start by making this diagonal. And I know a little secret here that I'm going to tell you, but we're going to prove it later, that if we draw sine accurately, it does not go above the y equals x. So this is y equals x. And if we draw sine accurately, it's going to live entirely beneath this thing. So it's going to look something like this and something like this. That's an accurate drawing of sine. It would not cross it like here. Okay? I'm not proving this right now, but it can be proved. So this is sine restricted to the interval. Here is pi over 2. Here is negative pi over 2. And the range is 1 and negative 1. Do you agree that this is my best hope for making an inverse function? Do you agree? Now I'm going to reflect it with respect to the diagonal. I'm going to get something that looks like this. Here comes the orange. Do you agree? Mirror image with respect to this line. And now the range and the domain change roles. So now this is pi over 2. This is, wow, tricky business here. This is negative pi over 2. This is negative 1. And this is 1. Good? So if you're all blurred from this, if you've never seen, and what is it called? It's called arcsine. Sometimes it's even denoted on many calculators. That's how it's denoted, like this: sine inverse of x. Have you seen this notation? Same thing, and that's where it comes from being the inverse function. Okay, and maybe just so you can see it without sine blurring the picture, this is what it looks like. It looks something like this. Not like x cubed. X cubed goes on up and down forever, right? This stops. This stops precisely at pi over 2, and then at negative pi over 2. Good? Okay. Moving on. I'm going to do the next two somewhat faster, because I want to have time to say one more thing afterwards. But if you want, you should, it's a good idea, a good practice idea, to draw them a bit more slowly and carefully at home. Okay? So the next two I want to draw are the inverse of cosine and the inverse of tan. But please do it more slowly and carefully at home. So cosine, if I want to take its inverse, I first restrict to an interval where it's 1 to 1 and onto. There it is, from 0 to pi. Do you agree that this is a chunk of cosine? Do you agree that this chunk is precisely a 1 to 1 and onto chunk? And now the inverse, this is a bit trickier. I have to look at this and draw the mirror image. And it's going to come out something like this. Okay, these two cross here. Okay, that's the inverse. It's called arc cosine of x, or same thing, cosine inverse of x, and it goes from, so cosine was bounded between 1 and -1, so this is going to be, well, I drew it a bit unaccurately. Let's make it a bit more accurate. Something like this. So this is going to go from 1 to -1 here, and the values are going to be from 0 to pi. So this is arc cosine. And the last one is going to be arc tan. These are the asymptotes of tan. Maybe let's do them in blue. All these appear on your handout with a bunch of functions. So, oh boy. So these are the asymptotes of tan at pi over 2 and at minus pi over 2. And tan looks like this. Kind of resembles x cubed, but x cubed can, the values of x cubed can be any positive x, where here we're, in order to be 1-to-1, we restrict just to one branch. There are more branches, right? So this is tan. And here's the y equals x thing. And this was pi over 2 and minus pi over 2. How many people are following me? Raise your hand if you're good, good. I'm happy to see that. Wonderful. So arctan is going to be a mirror image with respect to this, and it's going to look something like this, having asymptotes, having horizontal asymptotes at negative pi over 2 and pi over 2. So this is arctan of x, or tan inverse of x. We drew it earlier today, even. So is everybody good with these drawings and how I got them and why they came out like that and so on?
With the inverse cos function,
Uh-huh.
because goes to, like, the bottom y value is negative pi.
No. No, I started from 0 to pi. That's the chunk I inverted.
But what's the negative y value?
From 0 to pi, for the orange one.
No, for the...
From negative 1 to 1, because from 1 to 1 were the values of the blue one.
The cos function.
Okay, I have 5 minutes and I want to write one more thing. So come right after that and we'll discuss this and I'll explain, okay? Okay, so this is doing it graphically in order to do it, if somebody gives you a nasty function, cosine of x squared, all of that, e to the power, I don't know, something like that. And if you want to invert it, you have to write y equals that and solve for x. Do you know that? Have you seen that? Okay, so you'll have on the homework all kinds of exercises doing it algebraically, but I think that's just, you know, it's just technique. This is important. This is very important to know the graph-wise and to know these functions well. So what I want to do now is go back to the list of elementary functions and add the ones that I couldn't add before because we didn't know the notion of inverse function. So now we do, and we can complete that list. So if you remember, so elementary functions continued. So the fifth family is going to be roots, or more generally, inverse functions of polynomials. root x, root x, root cubed of x, and so on. The sixth family is going to be inverse functions of rational functions. Question. I'm going to leave it to you to figure it out. If you know the answer, don't yell it out loud. I want people to have an opportunity to think of this, okay? So if you know the answer, be quiet. Can you do that? Promise? Okay. What is 1 over x inverse? What's the inverse function of 1 over x? Okay? Don't say it now. Think about it. This is an example of a rational function, and I'm asking you what is its inverse. Okay? Think about this. Seventh family, inverses of exponential functions. And what are they called? Logarithms, right? So these are functions of the form let's call them g of x equals log base a of x, and the assumptions are the same as before. So a is positive and not equal to 1. And for these, just like for the exponentials, there are a bunch of rules governing working with these. Okay, and I expect you to know these rules from your past studies. And if you don't, now is a good time to review those or to learn them if you haven't, or if you forgot, if it was a long time ago. So, properties. We're going to be mostly working with the natural logarithm, which is logarithm base e. That's the one we drew. I just erased that example. Yeah, properties of logarithms. Okay, so for example, a to the log a of x equals what? X. This is just saying that those are inverse functions. You take x, you take the logarithm, then you take the exponent, you get back at x. Right? So it's not just a magic property. This is the definition of being an inverse function. That's precisely it. Likewise, log a of a to the x is again x. First do a to the x, take what you got, do a logarithm to it, you get back at x. And then there are a few more, like log a of x to the power b. You can pull that b as to the front here. Do you know this one, for example? Okay, and log a of a product is the sum of the logs. Do you know this one? Okay, dot, dot, dot. There are more of them. You should know these and feel comfortable with them. And if you don't, and if you're not feeling comfortable with them, please review them. Okay, you have to be at the point where these things don't scare you. Okay, you should feel friendly with these sort of things. And the last family, family number 8, is the inverse trig functions. Which we just wrote down. Arcsine, example, arcsine, arctan, etc. Okay? And now comes the definition, and with this we'll end up for the day. So, definition. An elementary function An elementary function is any function obtained from the above. The above meaning the above families 1 through 8. So any one of these lists, any function on this list, or one that is obtained from it using the operations that we mentioned, is any function obtained from the above families using plus, minus, multiplication, division, or composition. Remember this symbol?
Is a function that it's not?
Hmm?
Is a function that it's not an elementary function?
Okay, good question. So, are all functions in the world elementary? So this is the definition of an elementary function. Okay, any of these 8 families, or one obtained from them by, so for example, sine of log x, is that an elementary function? Yes, because it's sine composed with log x, right? So can you think of a non-elementary function? Right. Dirichlet, for example, is not an elementary function. There's nothing you can do to this list of elementary functions using these operations, plus, minus, times, divide, or compose, to obtain the Dirichlet function from these. In fact, the step function is not elementary either. And it's less pathological. Okay? So, most functions you can think of, most functions you've ever encountered are elementary, right? Because this definition is very, very, it kind of hugs everybody, almost. Okay? So Dirichlet is not elementary. Okay? Dirichlet and, for example, this function are not elementary. Question. Again, don't jump with the answer if you happen to know it. Is the absolute value of x elementary? Don't jump with the answer. Leave it to for everybody to think at his or her own pace. And okay, so let's end up here. This is a very good place to stop because we kind of finished the introduction to functions. Next time, the definition of the limit. Okay, drums, trumpets, and a lot of excitement. Okay, so happy Hanukkah to everybody.